So I have not put anything on Brightspace yet, but if you go to the assignments here on the sites, assignment 6 is already here. Okay, I'm just gonna add the link. I just ran out of time, okay? And I'm gonna run the solution for this assignment now because I believe it's important for you guys to check the solution so you understand what I'm expecting, okay? And this has to do with the clock, in case you're wondering. Let me just open the... You know, sorry to keep talking about this, but I just feel a bit, how can I say, sad about the results that I was expecting a bit more, to be honest. But I understand as well. But the most important thing in this course, and in anything that we do in life, is that we have to be consistent, and that seems to be like the most difficult thing. But anything that you do in life, you have to be consistent. You go to the gym, you have to be consistent. You want to learn something, you have to be consistent. You can't be like this, because it doesn't work. Yeah.
Well, if you're taking 6 courses and you have to touch on all 6 courses every single day, that's a pretty massive, like...
Yeah, no, I get it.
Cognitive load,
Yeah.
just to do 6 different concepts every single day. So
Yeah.
it's just like, how do you stay consistent while not burning your brain out at the same time?
Yeah. What can you do at that point? What do you do when you have too much on your pile? Like, because it happens to me all the time. I can tell you what I do.
Eisenhower matrix?
When I have too many things on my pile, unfortunately, at that point, I need to start prioritizing. And that may mean sacrifices. May mean that you have to reduce your load or drop one course or just decide to focus on 4 out of 5 courses, which sounds tough, but sometimes it's something that you have to do. You gotta, put the things on the table and then measure things and see what's more relevant, what's most important for you now, and then, yeah. I have students that lose so much class time. It's not the case of you guys, because they need to travel somewhere to whatever event, which is understandable, religion, family, whatever. But it's a choice, it's still a choice, right? So then my point is, if you make choices in life, you have to face the consequences of the choices you make. They cannot be transferred to someone else. We can understand, we can empathize, we can try to accommodate, but at the end of the day, it's gonna hit you. Because if you're not here in class, yeah, if you are prioritizing some other course, it's gonna hit you. And unfortunately, that's the decision that you're making. And it's tough. I get it. When you have 6 courses, which is why I feel like this program is ridiculously heavy for 2 years. Like maybe a smart thing to do is like to take a partial load and go through. But now that they're shutting down the program, they're making that a bit more difficult even. But, yeah. Life is tough. I get it. Okay, let's go through this. So the idea of this assignment is to complete the clock library and verify it. Okay, so we're going to use a system core clock variable which we've been using for a while, right? To check the settings. We're also going to use the MCO, stands for master clock outputs. That's one of the functions that we need to implement to see the clock on PA8 or PA9. Remember that we can use any of those two to see the clock outputs, and that gets configured through the alternate functions. We're also going to use PC13, which is the blue button, just to iterate through the different clock settings. We're gonna change the clock in runtime, which is something that most likely we won't do, but it's the best way to test that our functions are robust. So that means that the clock is gonna be running at a certain speed, and then when we press the button, it's gonna change the speed to something else. So it has to reconfigure the PLL, okay? That is different than configuring the PLL only at the beginning of the program and make it work, because a lot of things, when you first start the micro, are reset to the default values. Whereas when it's already running, it's already set to value. So it's important that you know how to undo or kind of de-init things, okay? And that's why the sequence Let me see if I'm missing something. Yeah. The sequence to enable the PLL is here. So we have to make sure that this oscillator is enabled, but to be fair, this one is always enabled. So if you don't touch it, it won't get disabled. This one is an internal oscillator, the HSI 60. Then here's the key that you haven't seen in my demos. See, because I cannot make the assignments 100% copy paste from my demos. There's got to be something that you have to add there to test your knowledge. And there's a line in the clock initialization where you set the PLL as the system clock, which is one of the last lines that you write. And when you want to change to a different PLL setting, you need to undo this, because you cannot turn off the PLL if it's being used. So you have to remove it and go back to this guy, sort of thing, and then only then you can disable the PLL. Because I did try this. I did try disabling the PLL while it's being used, and it doesn't work. It gets stuck there. So, after you disable the PLL, you wait for it to be disabled like we did, right? You write the new configuration with the M, the N, and the R. You enable the PLL, you wait for it to be set and ready, and then you switch back the PLL to the system clock. That's the sequence, okay? And you update this variable. And, well, there's a question here. Ideally, you want to put these answers in a markdown file, okay? I'm not going to be so strict with it, but this is part of the exploration that you have to do. Okay, so the first thing you got to do is what you've probably already done, which is filling out this thing. And I would like to, these were meant to be outside of here, so I will correct that later. So you have to fill out this part that is missing, which you probably already have, and code these two functions, which you probably already have. And then I want you to document the M, the R, the N, and the M that you came up with in the markdown file, like we've done it. And if you need help with this, it's just creating a table. We gave you I think I gave you one template.
Does that mean just like writing the value of each?
Yeah, you say for this one, so the table will have a column here, then an R, an N, an M. Nothing more, not this, just the values. I just want to see what values you came up with. If the whole class comes up with the same values, I will be a little suspicious. That's why. Well, because there are certain combinations, right? Yeah. Remember, I'm not doubting. I just want you guys to learn. That's all. The code two functions, and that will be ready. So after that, how are we going to verify this? Well, every time, so at the beginning, we're going to display, like we've been doing it so far, the system core clock variable. And every time the configuration changes, we're going to display it again. Okay? But we're going to display it in megahertz. So that means that whatever value is in this variable has to be divided by 1 million and then show megahertz. Only in the debug console, right? To keep it simple, because if it's in the USART, then you have to reconfigure the clock, the USART every time. You're going to enable the MCO line either on PA8 or PA9. It's up to you. But you're always going to use a prescaler of 8. So basically, you're always going to divide it by 8. So in a way that such that when you are at 64, you will be displaying 8 megahertz. When you are at 16, you will be displaying 2 megahertz, and so on. It will always be divided by 8, so we don't have to be dealing with the port speed. What I've noticed when I coded the solution for this is like if your flash settings are not properly enabled from here and up, your flash latency settings, remember? It breaks. So I suggest you put them inside your clock library, but just before you actually switch to the PLL. Okay, so this, because otherwise it will break here. Okay, so we're gonna create a feature where we're gonna cycle through all these different settings. My suggestion is that you put these enumeration values into an array. And then as you press the button, because you have to press a button to scroll through them, then you iterate through the array, and then you call the function and change the clock speed. okay? Once per press. So you're gonna have to use PC13 with a state, so it does it once per press. Because if you do it 1,000 times, you're gonna change the clock 1,000 times in a press. So that's gonna be tricky, okay? So once per press. And it works fine, the button is properly debounced. And as we scroll, we're gonna see the outputs change. All right, so then when you reach this one, you should wrap around and go back to this one. Okay, that's the, we're gonna use only one button. And that's it, I think. So I'm gonna demonstrate it to you guys now so you know what I'm talking about and what I'm expecting. Okay. Where is it? ICA 6. Oh, where is that running? That's interesting. Oh, because it's okay. So forgive me for not showing the main file for obvious reasons, but oh, but no, I don't find the okay debug. Okay, now I press play, and the clock is at 16 megahertz, right? I should probably turn on the other. It says here, that's it. No. That's one check you gotta do. The second check is going to show up on the other screen, where we should see 2 megahertz, right? Because it's always divided by 8, the output, okay? So then I'm gonna press the button once, take a look at the two screens, and it's gonna switch to 20 megahertz, and what's gonna show there is 2.5 megahertz because it's divided by 8. And the next press, so on, it's gonna show 3 megahertz. Why? Because it's 24. Then the next one is going to show 32 and 4 megahertz here. The next one is gonna be 5 and 40, 6 and 48, 50 and 6.25. Is that correct? Because I think I made a mistake last time. 12 and a half, 25, 50, yeah. 7.5 times 8 is 60, right?
Hopefully 60.
Yeah. And then lastly, 8 times 8 is 64, which is the maximum we can go. And then it wraps around. Now for this wrap around, see, for the first one that I showed, to be honest, I'm just using the default and I'm displaying at the beginning. But then when I wrap around, I call the PLL with 16, which is technically not the same. It achieves the same speed, but one at the beginning, it's just using the HSI. Then when I wrap around, it uses the PLL. So that allows me to also test that the PLL at 16 also works. And that's assignment. Any questions? If for some reason, when you're scrolling through this, you get stuck, the program gets stuck, it's because of something that's missing in there. Like I said, the hardware, the flash configuration, flash latency, or the disabling the PLL as a system clock before turning it off, and all that kind of stuff. So the steps are very important. That's why I describe the steps in the assignment. Any questions? No?
You said when we were we press the button, we wanna throw those enums that we have for our clock speeds in an array.
I feel like that was the easiest way to do it. You could do it probably with a switch case and whatever, but I feel like the array is probably the best thing to do, right? You just do it in a Carl is like looking at me. What's going on? Okay, So, did you get it working or you're still working on it? The clock, remember that something was not working for you yesterday?
65 right now.
Oh, you're kind of testing that now? Okay. This is the RCA. No, I didn't mean to open it.
If you'd like, I can go through and snip that out of the video before I post it if you'd like.
It's okay, you know why it's okay? Because that shows just a high level. Like the key part is behind the scenes, it's in the library. It works now?
Yeah, the error was like I just had it flash inside the code
Uh,
instead of the library. That's error.
Yeah, so
I
that's
just
what I'm
shifted
saying,
to
like
the
the
library
flash
and started
settings,
working.
they need to happen just before you enable the PLL as a
Yeah.
system clock. Otherwise, if you do it after, it's already too late, and then the flash gets stuck.
So I just shifted to library and then started.
And you can only notice that when you go 50 megahertz sort of thing and above. That's why I felt like it was important to scroll through every single setting to make sure that you can run your clock at any speed, because we don't want to see those problems later. Right? We're gonna get out of the way. Your clock should be robust enough.
So if you're not going to low power mode, why wouldn't you just set it to high speed and then just,
High speed?
yeah, for the pin?
Yeah, you could do that. The other instructor for this course, Simon, he likes to run always at 64 megahertz, which is the maximum. And honestly, if it was 80, I would run at 80. The other micros, the M4 series, those run up to 80. I just don't like 64 because when you do 1 over, the cycles are weird. Yeah, that's the only reason why I don't like 64. Okay. So the demo that we did for the timer, well, I should probably remove this from here now.
If you place it in your library, then
Yeah, because then it's gonna cause problems.
it'll get angry at you.
Yeah. So the system is running at 40 megahertz. I did this demo first using the simplest way of using the timer, using the update events. Now, I did add the lesson, although it's not quite complete, but it has at least a summary in case you want to revisit this. And now the table with all the timers is on the site. Okay. So remember, the timers can be used to generate delays and timeouts. They can be used also with interrupts. We haven't yet discussed interrupts. That's coming after. It can be used to generate a PWM signal, which is a variable duty cycle. And it can also be used to feed a signal and calculate the period of the pulse width of such a signal. Like any, let's say, Hall effect sensor or rotor encoder or ultrasonic sensor, anything like that could be used with a timer. That's why the timers are so important and powerful. Not just a simple counter, although that's the only thing that we use right now. This is looking like kind of weird. It's like kind of what? It's probably the angle on the projected screen. Anyways, this is the summary of all the timers that this micro has. And remember, we're starting with the basic timers, which basically can only count and roll over. That's it. They don't have any cap to compare channels, nothing. Okay? So that being said, the key things, and when I say key features, I'm talking about the registers that we need to configure. So the one that you always configure is the prescaler. So the prescaler basically divides the system clock to set the timer to tick at a certain frequency. So if your system clock is 40 megahertz, maybe you want your timer to tick at 1 megahertz only, in which case you need to prescale by 40. And that gets done in this register. You need to subtract 1. The other key register is the ARR, which is the auto reload register. If you don't write anything to this register, by default, the timer counts all the way up to the maximum that can be represented in 16 bits. How do I know it's 16 bits? Well, because it's on this table, right? Most of the timers are 16 bits. The only timer that is 32 bits is this guy, timer 2. So the maximum they can count is 65,535. But if for some reason you want this timer to count less, let's say make it a modulus 500 or a modulus 1000, whatever, you write a value on this register. So then you make the timer roll over early, let's say at whatever counts. All right? Then these other registers are for what's coming after. The cut to compare register, the gear register, as in interrupt enable, and this one has to do with the PWM modes that we're going to study at the end of the course. And there's also one pulse mode, there's complementary outputs. The timers are so versatile in this micro that we could be an entire semester studying the timers. So we're just going to scratch the surface, the most important features. So right now, we're mostly dealing with the update event, okay? And the update event is just when the timer rolls over. When it goes to the maximum ARR that you defined, or the default, FFFF in hex, and it rolls over. It generates this event. The other events you can have are the output compare events, which is where the counter is called actually CNT. Where the CNT equals the value that you write in this register, that's what's coming after. Or the other event is when you're feeding a signal in input capture that most likely we'll discuss next course. And then when that signal detects an edge, and the edge is detected like a rising edge or a falling edge, and then this event happens. So I wrote here the steps to use or to configure the update event only because that's the only one that we've been using so far. And the steps are very simple. First is to set the prescaler. That is what we do here. We make it tick at 1 microsecond because we know that we're running at 40 megahertz. So then we do 40 minus 1, done. It ticks at 1 megahertz or 1 microsecond tick. Means that the timer is just switching 1 microsecond, 2 microseconds, 3 microseconds. The ARR is the modulus number that we put in. When a modulus 1000 or whatever, in this case, this demo we wanted modulus 200, which is why we wrote 200 minus 1. And then we need to start the counter. That's it. Sometimes we need to update using this register. I'll talk about it later. Yeah, we'll have to generate an update event because sometimes the registers don't synchronize properly if the timer is already running. Yeah, so this event that we'll talk about later is basically to reset all the registers and the counter and start a fresh count. And then, the way we are doing this right now, because we're not using interrupt yet, we are pulling the update flag. The update flag is the one that gets activated when the timer rolls over, okay? When you reach the maximum value that we set up in the ARR register and roll over, it activates this flag. So when this flag activates, what do? You clear it by writing a 0 to it, using the mask, and then you do something, in this case toggle the GPIO to make sure that things are working, okay? We ran this demo, I think, 2 classes ago, but we're gonna run it again, just to verify. In case you haven't noticed, I'm going over this again, in case something wasn't clear.
Thank you.
Yeah, because this topic is 200. And now we take a look at the scope. We're only looking at the, why are we looking at the, because obviously, I'm not looking at PA5 anymore, I'm looking at the clock still. So
Different
I gotta
pin.
switch the pin. And now I'm looking at PA5, and I need to add the positive width here, because that's what I'm interested in.
There's a serious amount of ripple on that when you zoomed in.
Yeah, it's a bit noisy. Sometimes it's the setting of the scope because it was sampling such a high frequency signal, and now it came down. Yeah, 200 microseconds. Well, you could say it's 200.2 or 3, but yeah, it's accurate enough for what we're doing. What happens if I forget to clear the flag?
It's just set. You just stay in your loop. Nothing
Yeah, and
happens.
then see if the flag doesn't get clear, I keep going inside the if, and then the pin is gonna start toggling like crazy as fast as it can. That's not what I want.
It's stuck.
Now there's an alternative to do a blocking approach, which is this one. It's basically saying, well, just hold the code here in this line until the flag is active, and then go to this line, clear it, and then toggle it. Effectively, it causes the same thing, but we want to discourage you from using blocking delays because they're not good, because they block the code, right? However, because I got the question I asked yesterday, if the blocking delays are discouraged, why do we even cover blocking delays? That's a fair question, right? And the answer is that in certain situations, we may need a blocking delay. I'm going to give you one specific example. LCD initialization. In general, LCDs are super slow, in case you didn't know. They have an initialization sequence that you have to send a command, and then all LCDs are the same. Not the same sequence, but all of them are like you send a command, wait for 20 milliseconds. Send another command, wait for 120 milliseconds. And then at that point, you could do that asynchronously, but it will be too much work. And since you're doing that at the beginning of the code, the thing that it makes more sense is just to insert a bunch of blocking delays to properly initialize the LCD. So only in those cases we're going to need those blocking delays. That's why we study them. Because in the next term, or maybe by the end of this term, I'm going to give you an LCD, and I would like you to initialize it, and then you need a blocking delay function. Okay? That is consistent enough that can work with any clock speed. And that is the next example that I don't know if I don't think I've discussed this example with you guys. Let's take a look. But you know what? I'm going to open it in a second because it's lighter background. Okay. So it's basically the same demo as the one before, and maybe I can clean it up later because I got a bunch of things that I'm not using at this Hello World. And look what I did here. So I created a function, two functions. And guess what? I have two prototypes here because I need them, otherwise it won't work. So I said, well, what if I want to generate a 1 millisecond event, of 1 millisecond, using microsecond ticks? Because here's the thing, when you start thinking about this, there are many different ways. Before you even look at this, if I ask you and I say to you, with what you know now, can you generate effectively a 1 millisecond event? Okay? And then when it comes to that question, there could be many different approaches. You could say, you know what, I'm gonna make the timer tick at 1 microsecond and I'm going to count 1,000 using the ARR. That works, because that's gonna give me 1,000 microseconds, therefore 1 millisecond. But some other could say, you know what, I'm gonna make the timer tick at 1 millisecond. You can make it so, you can make a bigger prescaler and you can make it that every count is 1 millisecond. So then if you have a delay 50 milliseconds, then you count 50 times, right? So there are multiple approaches. So just so you know, the one I chose here was to create a function, just to demonstrate, to set the timer to 1 millisecond event by using microsecond ticks. Okay? So basically I'm gonna count 1,000. That's why I have this one here, right? See what I'm saying? Then why do I want to make it tick at microseconds? Well, because maybe I want to use a timer then to do an event at 200 microseconds, and then together with this, and maybe the microsecond tick is useful, whatever.
What happens if you have an event that has to happen on a faster time cycle than a millisecond?
Yeah, exactly. Well, in that case, you could probably use a different timer. But the other advantage of this, here's the thing. Because what I'm going with this is towards creating the same function that I created before, like that delay millisecond function, that could you input any milliseconds and it will work. But here's the thing, if you set the timer to tick at 1 millisecond, what is the maximum delay millisecond I can have?
Let's see. So
Well, it's actually quite large.
it's at 1 microsecond. I'm trying to think about the size.
Yeah, no, if you make it tick at 1 millisecond, then you can count 65,535 milliseconds, which is actually 65 seconds. That's a lot of time. Still a lot of time,
If you
right?
do it in microseconds, then you're
If you
looking
do
at
it in microsecond, it's only going to be
65
65 milliseconds. Yeah, that's what you know. But here's the thing. If I set an event that counts 1 millisecond based in 1,000 microsecond ticks, then I can call this in a loop, and I can just delay using software for whatever milliseconds I want. I just decided to do this because it will be similar to what you had before. Again, it's not the only way of doing it, and I'm going to show you different ways later. But this one is just basically setting the timer to generate a 1 millisecond event. You know what? I'm going to write this here. This function generates a 1 millisecond oh no, 1 millisecond event using 1,000 microsecond ticks, right? Via ARR, auto reload register, okay? That's what it does. Now, the question is, why do I have system core clock divided by 1 million minus 1? And I say 1 microsecond tick.
Is that operating off the basis that we're looking at the base level clock speed? Or
Yeah, before when I did the microsecond tick, remember that I hard coded a 40 minus 1? Because the system was running at 40 megahertz.
This one's running at
Then if it's running at 16, I will hard code at 16 minus 1. If it's running at 64, I'll have to hard code at 64 minus 1. But that happens to be the core clock divided by 1 million. That's what it is. So what this is telling me, that if I implement it like this, it's going to work for any clock speed. And it's always going to give me 1 millisecond. Do you agree or not? Because it's using this variable.
Yeah.
If you, let's do the exercise.
Okay.
If you are running at 40 megahertz, system core clock is 40 million. Divided by 1 million gives me 40. That's a good number. If I decide to run at 64 megahertz, that is 64 millions. Divided by 1 million is 64. That's a good number. That's the number I need to prescale by to tick at 1 megahertz. Now, if I wanted to tick at 1 millisecond, so 1 kilohertz, all I needed to do is just do 3 less zeros, right? And then it will also work for any clock speed. That is the advantage of doing it like that. Provided that your system core clock variable gets updated accordingly, which is why it's important that inside your clock function, you call system core clock updates at the end, okay? Is that clear or not?
So 16 megahertz core clock divided by 1 million, that gets us 16.
Yeah.
Then you minus 1.
Well, it's always minus 1 because that's the way the prescaler works, right?
Yeah.
So if you look at this previous demo, let's take a look here. You're doing a 40 minus 1. And the reason why you're doing 40 minus 1 is because you're running at 40 megahertz.
Gotcha.
Yeah. So if you were running at 16, you will have to do a 16 minus 1. Because basically you want it to tick at 1 megahertz. That's the goal. Okay.
Okay.
Once I have this one, well, the first thing I want to do is comment out this. Oops. Because this comes after. Oh my goodness. Just pretend this thing doesn't exist, please. How am I going to test this? Well, I want to toggle the GPIO, right? Which is, oh, this guy.
Already there.
Oh, sorry. Never mind. I'm being stupid. What is this function called? Oh,
Set timer millisecond.
yeah. So here's the thing. This function set timer is just setting the thing, and this is starting the counter. Okay. So now, how do I check that the event actually happened? I need to do the same check that I did before. If timer, which timer is this? 6?
6.
Pointing to ISR. Is it ISR or SR? And timer underscore SR underscore update flag. If that happens, what do I need to do? Clear the flag. I
And,
clear it by writing a 0 to it,
and then you would toggle.
and then I toggle inside. Yeah. Now, this is exactly the same thing that I did before. Then why did I create this function? Because I'm trying to help you so you can create your libraries later, right? So this is going to prepare the timer to generate a 1 millisecond event, but the actual check has to be done here still. If I run this thing, and if the LED toggles at 1 millisecond, that's going to prove that my 1 millisecond event works. And it does work. Well, I'm off by 1 microsecond, but that's acceptable. So like 1 or half a microsecond. Okay? Here's the important thing now. If I go and change my clock, well, my clock is actually running at 64 right now,
Yeah.
in case you didn't notice. I'm going to make it run at 40. And it still works. I make it run at 25. Do I need to keep going? I don't think so. Oh, I don't have a 25? What do you mean?
No, you have a 24 though.
Oh, 24. Yeah. Okay. I should have added a 25.
You still can.
Yeah, there you go. And it still works at 1 millisecond. In fact, you could have this function in fact, I should have added that. Oh no, because that's not part of the clock library. Then you could run the different clocks, right? And run this function, it should still work. However, every time you change the clock, you will have to recall this function, because that's the one that sets the proper prescaler, see? So the order of events is important. But what I proved here is that this 1 millisecond event works for any clock speed that I decide to have. So I'm going to stay with 40 for now. Now, once I know how to generate a 1 millisecond event, I could generate an event that is X milliseconds, a blocking event in this case. And that is the function. See, this is similar to what we did before. This is now using the new millisecond event function. And I did this in a strange way, so I hope I don't confuse you too much. So you're gonna pass in a milliseconds. And that milliseconds is gonna be any number. Let's say 100, 25, 51. And then you're gonna say, while milliseconds, you're gonna do something. And then you're gonna decrement milliseconds until you reach 0, right? Because when this is 0, then it's gonna exit this one. And what you're gonna do is you're gonna be in here and check if the flag is active, means that you do have the 1 millisecond event, right?
Then clear the flag.
Clear the flag and decrement the variable. So now when I replace this thing, so I remove this, you know what? let's do what you guys like to do. Define, how we define this one? Advanced.
Setting up macros.
Okay, so you know what? This thing, you can actually do this. I don't know if you knew this. You could do, if not defined advanced, do this code. I think it's called else. You can do an else if. I'm not sure if you can do. Is it E? I think it's elif. Yeah, there we go. We're getting very advanced here.
So
the
you have
keyword-
if statements as macros now.
Yeah. Delay for whatever milliseconds I want. In this case, I said 65. Why not? And then toggle. I don't think it's gonna work actually. It's complaining about something. What is he complaining?
Yeah, I think.
Error. Expected value in expression.
Well, because
Oh.
advanced hasn't been.
Okay. Would it be this?
Well, also.
Oh, well, there you go. No.
It's complaining because there's no value that's been set to advanced, I believe.
No, I noticed you did that in your exam. There's no need. Because there's just macros. Come on. Huh? I don't think I need a bracket, to be honest, but we can add a bracket just to see if that's the case. I wanted it to work, come on. I've used the elif before, but there's something I'm missing. You know what? Let's search it out. Yeah, the elif is equivalent, elif, constant expression, code block, and then an if. That's what I'm doing. Oh, okay. If not defined advanced, elif advanced. Oh, but elif def. There we go. Okay, I think that's the one I wanted to use. Well, you know why I'm doing this? I've just been. It's just because I don't want to use two defines. That's all. I just wanted to use the one. Yeah, I think that's correct now, right? Although it doesn't kind of like this one. It says that the use of elif def directive is a C23 extension. Oh. So in order for this to work, I need to use C23.
And what version of C are we running on in Segger?
We are probably running.
C22, C21?
Where's the compiler? C99. We can go up to C17. But I think it's still gonna work. Otherwise it wouldn't be showing this. Let's try it. Yeah, it's working. Yeah, we can deal with that later. I don't know. 65 milliseconds. So now I can put any number in here, any millisecond number, and it will work. I can do 25, for example. Now this is a blocking delay, right? And again, you could use something like this for initializing an LCD or something. See, now it's doing 25. Okay? If you wanted to do a non-blocking millisecond event, you could probably make the timer tick at millisecond and do a similar thing. Oh, we went over the break all this time? Yeah. Okay, but I'm going to show you that later. I think I should call it a day here, or you want me to keep going?
Up to you, sir.
No, you guys need to tell me if you need time to work on your stuff. Do you need time to maybe ask questions? What? Okay, so we're gonna break it here. The next on Friday, I'm gonna do one last demo because I want to move on to the other topic. The update flag is I think is good enough already, but then maybe this could be a challenge for you guys. What if I want to do this millisecond event, but not with a blocking thing, with non-blocking? So one way you could do that is instead of setting the millisecond like this, instead of setting the set timer millisecond event, you could create a function that sets 1 millisecond tick. So basically that does this, similar, but so now the timer it ticks at 1 millisecond. And then in the check here, you're gonna check for this flag in here, right? And every time you check it to be active, you're gonna clear it and you're gonna count 1. You keep counting and that will give you the same thing, for example. Or you could set the ARR to the value in milliseconds that you want, and that would be only one event. I think actually that would be better. But we will discuss it next class. But if you want to play with this for now, find a way to sort of like creating the same thing, but in a non-blocking fashion. So it doesn't block the code here for 25 minutes. Okay? Check off?
Yeah, the parts you achieve.